For this project, we will be gathering our data from a survey performed at the beginning of the semester for this statistics course. I believe this is across a few classes. And I also believe this is a required course for the college, so we can assume that the students in these classes have an array of majors. Although we can also suspect that since it is a required course, a large number of the students in this statistics course may be first-year students or maybe returning students, although that is not necessarily the case. But for the sake of this project, we will go ahead and assume that the sample data we obtained from this survey is a fair representation of the student population at Ventura College. For this specific project, we went ahead and gathered 5 questions to help us analyze if age, hours of note-taking, and hours of study make a difference in a student's GPA. The first question is, how old are you? I'm 20, I'm 30. The next 2 questions, I wish they had specified a whole number. They are, how many hours a week do you note take for exam quiz preparations, or how many hours do you study in a week? Unfortunately, this left it up for interpretation. There was a lot of answers with that were not numerical, I should say, and there was a lot of answers with ranges. So that might be a bit of a problem. And also the next question, what is your grade point average? That is a straightforward question. If you know your grade point average, it might present a problem if this is your first class. If you're a high school student taking some college courses, these are your first courses and you don't know your GPA, or you don't have a GPA if you're just starting college. So that might be an issue. And also our last question is, when it comes to note taking, do you feel like it improved your grades? When gathering our data and cleaning up our data, we came across a few issues. I'm not sure if there was a software error or there was a user error, but it seemed like our survey results data was compromised. As you can see from question 12, there was a few question results in there that were missing entries. And also a lot of the questions in the survey did not correspond to the question results in the survey results. As you can see from question 59 through 63 in our survey, those questions correspond to the question results of 80 through 86 in our survey results. So you had to do a lot of sifting through the results to connect the correct question results to the correct question in your survey. So that can create an error if you chose the incorrect results for your question. And also, we can't be sure that the results that we did obtain for our questions are correct due to the error. Now, when cleaning up our data, there was a lot of entries that were unusable. As you can see from the question, student grade point average, I am not sure if the respondent did not have a GPA or did not know if they had a GPA, or I am not sure what they were doing, but they wrote in what appears to be an 86.7, which appears to be a grade for the class instead of a grade point average. There's also a few other respondents that did not provide a number or a grade point average, or they wrote in a letter grade instead of a grade point average, or they wrote in a quantity above a certain number, which we can't know if is it 3.2, 3.6, 3.8. So unfortunately, that is unusable. There's also, if you see at the hours of study questioned, there are a few respondents that did not write a number. As you can see from a little, that's something that we cannot know. Is it 1 hour? Is it 2 hours? Is it 3 hours? And a few also wrote in ranges. As you can see at the bottom, 12 through 16. If we modify that to 12, it's going to alter our results. If we modify that to 16, it's going to alter our results. So there was a lot of entries that were unusable, unfortunately. We started with a sample size of 90, and at the end, once we remove the unusable entries, that was reduced to around a sample size of 60. And which is unfortunate. That's a huge loss of data points for our analysis. So, and as we know, a small sample size may not provide a true representation of the population parameter that we're after. So that can create an issue down the line. The first thing we're going to analyze is the age of our students in our data set. As you can see from the summary statistics at the bottom, we initially started with 90 sample size. And once we removed those data points that were unusable, those entries that did not provide a true GPA, we were left with a sample size of 61 Ventura College students. Now looking at our data, we can see that our data is skewed to the right, likely due to these outliers to the right of our box plot. And we can also tell that the majority of our students are aged between 15 and 25 years of age here on our histogram. And the middle 50% of our data is between 18 and 21 years of age here on our box plot, as we can see here from quartile 1 and quartile 3 on our summary statistics. Now looking at our variance, we can see that both sample sizes have a high variance, and variance just tells us the spread of our data. So it's letting us know we have a high spread of our data. But looking at our graphs, we can see that most of our data is concentrated to one side. So it's likely that our high variance is affected by the outliers. Now looking at our median and mean, we can see that the median is the same for our large sample size and our smaller sample size, but the mean changes and it becomes more or greater for our smaller sample size. And this likely means that the data points that we removed because they were unusable were closer to the mean and to each other. And that's why now our outliers are pulling our mean higher and our variance higher, which also tells us that our mean is less resistant to outliers than our median, which remained the same for both sample sizes. And on a side note, this red line on our histogram is a representation of our median, and our green line is our mean. And for the sake of this project, we are going to go ahead and assume that the data provides an accurate representation of the student population at Ventura College. The next thing we're going to analyze is hours of study per week for our sample set of students. As you can see, our sample set for this set is 57. Which is less than our sample set for age of 61. And this is due to some students providing the correct sample for, or entry, I should say, for age and GPA, but not providing a correct entry for hours of study per week. There was a few entries in there that were unusable, as some just wrote it depends, or they did not provide a number. So our sample size was reduced to 57. And as you can see from the graphs, this is our data is also skewed to the right for this set, and this is likely due to the outliers you can see here on the side of our box plot. And we also have a large variance, likely due to outliers. As we can see, the variance here is high, but the middle 50% of our data is between 5 and 14 here on our box plot, and our max value point is 40. So it's likely that the outliers are affecting our variance. And we are going to go ahead and assume that this data provides an accurate representation for the student population of Ventura College for the sake of this study. As we're having a high number of outliers skew our data, I just want to do a quick side note on outliers. As you can see, I went ahead and removed any outliers above 25 for hours of study. And that greatly reduced our variance. As you can see here, our variance went from 66.87 to 24.54. And it also almost halved our standard deviation from 8.17 to 4.95. And our mean didn't change too much. It went from 11 to 9, and also our median went from 10 to 8. So removing those outliers greatly affected our variance and our standard deviation. And as you can see from our histogram, it provided a more symmetrical shape than before. So it does kind of give you a cleaner data set to analyze, but removing any outliers, it may decrease the accuracy of your results. If those outliers are true data points, are data points that represent real values for your population. And it also may create bias as you're removing information that represents a true value, although it may be extreme, of the population that you're trying to analyze. The next thing we're going to analyze is hours of note-taking per week for our sample set of students. As you can see here, we have a sample size of 60, which is higher than the sample size of hours of study, which was 57. And this is just because we had a higher amount of entries that were usable for hours of note-taking, which just means that students provided a usable entry for GPA and a usable entry for hours of note-taking at a higher amount than students who provided a usable entry for GPA and a usable entry for hours of study for the previous set. Now looking at our graphs, we can see that our data is skewed to the right, likely due to these outliers here. Also on our histogram, you can see that it's still skewed to the right, but our data is a little bit more spread out. And also our variance, although still high, and our standard deviation, although still high, it's less than our previous data sets of age and hours of study. And this might be likely due to having less outliers for this data set and less extreme outliers as well, since as you can see here, our max is just 15. So based on the data here, we're going to go ahead and assume it provides an accurate representation for the hours of note-taking for the student population of Ventura College, which I just realized I should have been specifying that as well for the previous data sets. So I apologize. But on a side note, we also used another survey question. And this one asking if students felt that taking notes improved their grades. And at a frequency of 56, 56 students said yes, that you do feel that note-taking improves their grades, and that is and that equals to 93% or 93.3%. That is around 93% or 93.3%, excuse me, of students saying yes, that they felt that note-taking improved their grades. And now we're going to analyze the student GPA for a sample set of students. And here our sample set is 61. And this is going to be the variable that we are going to be testing the relationship against age, hours of study, and hours of note-taking. So as you can see from the data, from the graphs here, our data is skewed to the left here, likely due to outliers, and our histogram shows a somewhat spread of data, but it's a little bit more symmetrical than the rest. It's a little bit more bell-shaped than the rest, than the previous data sets. And as you can see here, we have a low variance and a low standard deviation, which there's not, which just says there's not a lot of spread of the data. And as you can see here, the median is 3.5 and the mean is 3.4, which is, it's fairly close. So we have a low variance here. And based on the data, we're going to go ahead and assume it provides an accurate representation of the student GPA for the student population at Ventura College. Now on to confidence intervals. One of the questions used for this project is, what is your grade point average? And a grade point average is quantitative data as it is measurable. And here we're going to try to compute for the confidence intervals for the mean grade point average of all Ventura College students. And we're going to try to do so at a 95% confidence level. And at the 95% confidence level, it just means that you expect the results to fall within those confidence intervals at 95% of the time. And you expect the results to fall outside of those confidence intervals at 5% of the time, so a 5% error. So here we're first going to go ahead and check our assumptions. We already know that our student GPA sample size is 61 from our previous chart. So we know it is higher than 30, but our box plot here shows that we do have outliers. So we can go ahead and check for the normality or normal distribution using our histogram and our QQ plot. And here I am using the QQ plot. As you can see, it is fairly linear towards the middle. But it sort of falls off the rails towards the edges. So it seems that it is not normally distributed. So we do not meet the assumptions for this test for the confidence intervals. But just for the sake of this project, we're going to go ahead and compute for them anyways. So at a 95% confidence level, once we go ahead and use StatCrunch to compute that with our data, we see that here our confidence intervals are 3.2968 and 3.5225, and rounded out to the second decimal place, that's going to be 3.3 and 3.52. And the results also provide you the point estimate right here, which just is the best guess or best estimate of your unknown population parameter. And here we can go ahead and subtract one of the confidence intervals or both confidence intervals from the point estimate, rounded out to the second decimal place. And here we're just going to do 3.30, and that's going to provide us the margin of error. So here, based on our results, we can say that we are 95% confident that the mean grade point average for all Ventura College students fall between 3.30 and a 3.52 grade point average with a 0.11 margin of error. You can also compute the confidence intervals for a lesser confidence level. As you can see here, at a 90% confidence level, but this usually narrows down your interval range. As you can see here, it's 3.31 and 3.5. So that also means that you have a more narrow margin of error. So if you go ahead and subtract 3.32 from 3.41, you're going to get a margin of error of 0.9. Excuse me, 3.32. So this just tells you that you might have a more accurate, obtain a more accurate answer within those intervals, but you are not as confident about your answer since there is a 10% margin of error here. And also, so when you're trying to compute for your true population parameter, you will try at least to use a wider interval range. That way you are more confident that your answer is going to fall within those confidence intervals. And on to correlation. Here we're going to go ahead and try to analyze if there is a relationship between our two quantitative variables, which is really just our two measurements on the same object, that being students, and also to determine the strength of our linear correlation between our two quantitative variables. And to do so, we're going to go ahead and use our correlation coefficient right here, which is our R value that falls between -1 and 1. And so the closer our R value is to 1 and -1, the stronger the linear correlation. And the closer our R value is to 0, the weaker the linear correlation. So the first two quantitative variables we're going to try to analyze are our students' age versus our students' grade point average. And to do so, first we have to check our conditions for a linear regression, which is that you have a set of XY ordered pairs if that set is a random sample from the population of all possible XY pairs, and which we do. We do have a sample of a random sample of students, and here it is, we have a random sample of 61. And our next condition is if our scatter plot of X versus Y, if that data shows roughly linear, a linear pattern with no outliers, which it is not. If you see here on our plot over here, it has a lot of outliers and it's not linear at all. But for the sake of this study, we're going to go ahead and compute for the correlation. And to do so, we're going to use StatCrunch. We're going to go ahead and test for our linear correlation coefficient with our data. And when we do so, this is the results that are provided. So if you see here, this is our regression equation, which also provides our line of best fit over here. And it also gives us our R value, which is our correlation coefficient. And as you can see from both the R value and the plot over here that we have, there is a weak correlation. As you see, the spread of the data is not around our line of best fit. It's just a little bit all over the place, and we do have a lot of outliers. And also our R correlation coefficient is a negative number, negative 0.2725, which is closer to 0 than it is to -1, which tells you that it is a weak linear correlation and also a negative linear correlation. So as you see on our graph here, the line trends down, which also tells you it's a negative correlation, and the spread of the data tells you it is a weak correlation as well, since it's not centered around the line of best fit. So what you can say is that the student's GPA decreases as the student's age increases based on this line, but it is a weak linear correlation due to the low number of our R value and also to the spread of our data in our graph. But we also have to note that the results are likely influenced by our outliers. And that's something that I can definitely believe that there might be some correlation between a lower GPA for an older student, since maybe they have jobs, or they have kids, or they have a different lifestyle than a younger student. So I can see that possibly being true if there is some sort of correlation there, but based on our data here, it does suggest that there is a weak linear correlation between the age and of our students and the students' GPA. So the next two quantitative variables we're going to go ahead and analyze are our students' hour of study per week and our students' grade point average. As you can see from the graph that we have here, our data points are very spread out, and they're not roughly linear, and there are a lot of outliers to the side. These two variables don't meet our second condition, but for the sake of this project, we're going to go ahead and compute for the correlation. And once we do so, we are provided our regression equation right here, as you can see, which provides our line of best fit over here. And as you can see, our line is slightly pulling up for a positive correlation, but it is almost horizontal, which you can see here from our correlation coefficient. It is a 0.131, which is very close to 0. So this is a weak linear correlation between our students' hours of study per week versus our students' grade point average. But it is likely, the results are likely influenced by outliers. And for that, I went ahead and I wanted to check to see if there was any difference without our outliers. So I went ahead and removed at least all our outliers above 25. And as you can see here at the bottom, once we compute for that, we get our regression equation here and a line as best fit. And our line on this graph is almost horizontal. As you can see, it's almost a horizontal line, which means it's close to 0. And as you can see here from our R value, that is a 0.11. So that is really close to 0, which means there is a weak correlation. And even if our R value was 0, it does not mean that there is no correlation. It just might mean that there is no linear correlation. And as you can see from the spread of our data on both graphs, our data might not even be linear at all. So from the results of this data, what we can take is that as our R value is 0.131, which is really close to 0, and that way it suggests that there is a weak linear correlation between our hours of study per week for students and our students' grade point average. So the last two quantitative variables we're going to go ahead and try to analyze are a student's hours of note-taking per week and its student's grade point average. And I don't believe I mentioned this before, but the dependent variable is a student's grade point average, as you can see here. And our independent variable is a student's hours of note-taking per week. And here we're just trying to measure the response for our dependent variable when there is a change in our independent variable. And a student's GPA was the dependent variable in all of our sets, or is the dependent variable in all of our sets. But like our previous sets, these two quantitative variables do not meet the second assumption. So as you can see from our graph over here, our data does not resemble a roughly linear pattern without outliers. There are some outliers here. So we do not meet the second condition, but we will go ahead and compute for the sake of this project. And once we compute our data using StatCrunch for the linear correlation coefficient, we are given our regression equation, as you can see right here, which provides our line of best fit. And as you can see from our line, it's slightly pulling up, which tells us that it's a positive correlation. But as you can see from the graph, based on the spread of our data, it looks like it's a weak correlation. Actually, the spread of our data kind of looks like there is no correlation. But as you can see here from our R value, which is 0.2015, that is a number that is closer to 0 than it is to 1. So this is a weak linear correlation. So based on our data here, what we can say, or what our R value of 0.2015 suggests, it's that there is a weak positive, which I should have written here. There is a weak positive linear correlation between a student's hours of note-taking and a student's grade point average. And also, obviously, the results are likely influenced by our outliers. Now that we have described our data and tested to see if there is a relationship between our quantitative variables and determined there is a weak linear correlation between them, or a weak relationship between our quantitative variables, now we're going to go into hypothesis testing, which is the purpose of this project, to determine if the mean grade point average for Ventura College students is affected by their age, by their hours of study per week, and or by their hours of note-taking per week. And to do so, we're going to go ahead and do our hypothesis testing for independent samples of two means. The first hypothesis testing we're going to do is for our variables of a student's age and a student's GPA. And as you can see here, we went and divided our sample size of 61. If you remember from our previous slides, our sample size was 61. So we went ahead and divided it into two groups. And group 1 is students aged 15 to 20. Group 2 is students aged 21 and up. And as you can see, a large part of our data, or a large number of our students in the sample size are between the ages of 15 and 20. As you can see here from our sample size of 44. And for our sample size for group 2, students aged 21 and up, it is 17. We went ahead and computed also for the mean, the sample mean for our GPA for group 1, which is just counting up all the GPAs in this set and divided by n, which produced a 3.47 for this group, as you can see here. And we did so for the group 2 as well, which we determined was a 3.26 for the sample mean of the GPA for this group. So our null hypothesis for this test is going to be that there is no difference between the mean grade point average of students aged 15 to 20 versus the mean grade point average for students aged 21 and up at Ventura College. And as you can see, our null hypothesis is over here. Alternative hypothesis is that the mean grade point average of students aged 15 to 20 at Ventura College is higher than the mean grade point average of students aged 21 and up at Ventura College, as you can see right here. Now that we have our groups, we're going to go ahead and test for our assumptions. And the first assumption is if this is a random sample, which it is for both groups. And then we're going to test to see if they are independent, which they are. Group 1 does not affect or make a difference in Group 2. And then we're going to go ahead and test, since we don't know the standard deviation, we're going to go ahead and test if this is a normal distribution for each group. And for that, we can go ahead and use our histograms, our box plots, our QQ plots. And here I inserted a few. As you can see, for the first group, there is outliers. Even though the sample size is above 30, they do have outliers. And as you can see too from the QQ plot for group 1, it seems roughly linear, kind of. There's a few points that are a little bit out, but it sort of goes off to the sides here on the ends. So we can determine that this is not, or probably suspect that this is not a normal distribution. And also for group 2, the sample size is less than 30. And as you can see from our QQ plot, this is not roughly linear at all. It sort of goes off to the sides here and off to the sides here and off to the sides here. So it's sort of dancing over the line. And although our box plot showed no outliers for group 2, which unfortunately I couldn't insert in here, the other assumptions are not met. So we can determine, or at least suspect, that this is not a normal distribution. But for the sake of this project, we're going to go ahead and compute anyways. So as you can see, we went ahead and computed our data through StatCrunch with a 2-sample t-hypothesis test. And as you can see, here is our group 1 and our group 2. And once we went ahead and computed that data, you can see that we have a p-value here, and we have a t-stat here, our test statistic right here. And we also have our sample statistic here as well, which is just the difference between our group 1 sample mean and our group 2 sample mean. So as you can see here, if we subtract the other sample mean from group 1, we're going to go ahead and get 0.21. And since our sample means were rounded to the second decimal place, as you can see here, if you round out to the second decimal place, you're going to get the same result, 0.21. Using the standard significance level of 5%, or alpha 0.05 over here, we're going to go ahead and interpret our results using our p-value here. And what we can say based on our p-value is, since our p-value is greater and or equal to the level of significance of 0.05, we fail to reject the null hypothesis, which means that we conclude that there is not significance evidence to support that there is a difference between the mean GPA of younger students at Ventura College and the older students at Ventura College. So there is no difference between the mean grade point average between all students aged 15 to 20 and students aged 21 and up at Ventura College, which is something we suspected based on our correlation results, since we found out there is a weak correlation between these two quantitative variables. And I should have written all younger students at Ventura College here and all older students at Ventura College. Now we're going to go ahead and do our hypothesis testing for our next set of quantitative variables. Here it's our students' hours spent studying per week, and the student's grade point average. And what we're trying to find out or determine is if the number of hours spent studying per week affect a student's grade point average. So we're going to go ahead and take our sample size for these two quantitative variables. If you remember, that sample size was 57 from our previous slides. And we're going to divide that into two groups. Group 1 being students who studied 12 hours or more per week, and then students who studied less than 12 hours per week. And that gives us a sample size of 22 for group 1 and a sample size of 35 for group 2, which together makes 57. Next, we're going to go ahead and determine our mean, our sample mean for the GPA, which is just summing up all our GPAs and divided by our number, or 22 here. So that is a 3.52 for group 1, and that would be a 3.39 for group 2, as you can see right here. Now that we have our groups, we're going to go ahead and give our null hypothesis and our alternative hypothesis. And our null hypothesis is just that the mean grade point average of students at Ventura College who study 12 hours and up is equal to the mean grade point average of students at Ventura College who study less than 12 hours. Our alternative hypothesis will be that students who study 12 hours and up have a greater grade point average than students who study less than 12 hours per week. So now we're going to go ahead and check for our assumptions. We already know this is a random sample, and they are independent since group 1 does not affect group 2, or they have no relationship. And we don't know our standard deviation, our population standard deviation. So we're going to go ahead and check to see if our groups are normally distributed. And we're going to go ahead and use our histograms, our box plots, our QQ plots. And as you can see here for group 1, for their histogram, it does show a sort of a bell shape, so it seems fairly normally distributed. And their QQ plot, it seems roughly linear. The data points are mostly over the line, so we can suspect that it is normally distributed, even though the sample size is less than 30. And for our group 2, our sample size is greater than 30. So, and when we check our box plot, there is no outliers. So we can go ahead and assume this is also normally distributed. And then we can go ahead and compute our data using StatCrunch with our two-sample t-hypothesis test. And when we do so, we get our p-value here, our test statistic here, and our sample statistic here, and which we know is just the difference between the sample mean of group 1 and the sample mean of group 2. So if you subtract here the sample mean of group 2 from group 1, you're going to go ahead and get 0.13. And if you check here, this is rounded out to the second decimal spot. If you round out here as well, you're going to get the same results, 1.13. And now that we have our results, we're going to use a significance level of 5% or 0.05 and our p-value here to give a conclusion based on this data. So we're going to go ahead and say that since the p-value is 0.1138 and that is greater than or equal to our level of significance of 0.05, we fail to reject the null hypothesis. So we conclude that there is not significant evidence to support that the mean GPA for all Ventura College students who study 12 hours and up per week is higher than that of Ventura College students, of all Ventura College students, I should say, who study less than 12 hours per week. And this is something that we suspected based on our correlation results, as that found that there was a weak relationship between these two quantitative variables. So this is not very surprising. So now we're going to go ahead and do our last hypothesis test on our remaining two quantitative variables, which are the student's number of hours spent note-taking per week, and also the student's grade point average. And we're going to go ahead and take that sample. If you remember from our previous slide, the sample for these two quantitative variables is 60. And we're going to divide that sample size into two groups. Group 1 being students who note-take 6 hours or more per week. Group 2 being students who note-take less than 6 hours per week. And as you can see, we're going to have a sample size of 18 for Group 1 and a sample size of 42 for Group 2. Then we're just going to go ahead and solve for the mean sample, or the sample mean for each group for the GPA. And again, that is just summing up all of our GPAs for each group, or summing up all the GPAs for one group and dividing by n for that group, which gives us 3.52 for Group 1 and then 3.35 for Group 2. Now that we have our groups, we're going to go ahead and state our null hypothesis and our alternative hypothesis. Our null hypothesis being that the mean grade point average of students who note-take 6 hours or more is the same or equal to the mean grade point average of students who note-take less than 6 hours per week. And our alternative is that the mean grade point average, of students who note-take 6 hours or more per week is higher than the mean grade point average of students who note-take less than 6 hours per week. And we're going to go ahead and check our assumptions before we compute our data. We already know this is a random sample, so we're just going to check to see if it's independent. The groups are independent, which they are, as Group 1 does not affect Group 2, and our population standard deviation is unknown. So now we're just going to check for the normal distribution for Group 1. As you can see, it is less than 30 for a sample size. And if you see with our QQ plot, it is not roughly linear. The data points sort of do a little squiggly line over the line there. And then for Group 2, we do have a sample size greater than 30, and as you can see from our box plot, there are no outliers, so we can go ahead and assume or suspect that this is normally distributed, unlike our Group 1, which we suspect is not normally distributed. Although our Group 1 did not meet our assumptions, we're still going to go ahead and compute our hypothesis test for the sake of this project. And then we're going to go ahead and take our data and compute with StatCrunch using our two-sample T hypothesis test, which provides us with our p-value, our test statistic, and our sample statistic. As you know, the difference between the sample mean for Group 1 and the sample mean for Group 2 is our sample statistic here. So if you divide here Group 2 from Group 1, you're going to get 0.17, and this is all rounded out to the second decimal spot or place. And if you go down here, you're going to see that that rounded out is also 0.17. So now that we have our data, we're going to go ahead and use a level of significance of 5%, which is 0.05. And we're going to go ahead and use our p-value to make a conclusion on our data. And we can say that based on, as our p-value is 0.082, which is greater than or equal to our level of significance of 0.05, we fail to reject the null hypothesis. So we conclude that there is not significance evidence to support that the mean grade point average of all Ventura College students who note take 6 hours or more per week is higher than all of the Ventura College students who note take less than 6 hours per week. And again, this is something that we suspected based on our correlation test, which determined there was not a strong relationship between these two quantitative variables. It determined that there was a weak linear correlation between them. So this is not something that is surprising. And I forgot to mention though, this is a ride-tail test, as you can see here. And I believe that is the case for the other hypothesis test as well. Based on the hypothesis testing and the correlation testing, it seems that hours of studying, hours of note-taking, and age don't have as much of an effect on a student's GPA based on our sample set than what I thought. It just showed that there is a weak enough relationship between them for it to be just a coincidence. Which was not what I was expecting. I was at least expecting studying to have at least somewhat of an effect there, since I'm assuming when people are studying, their version of studying is also taking quizzes or doing the examples, which I believe help in retaining information when you're doing the examples in your courses or doing solving problems for what you're studying. But some of the entries did have some students mentioning that they were studying, but they were not note-taking. They had 0 as note-taking hours. So I'm not sure what type of studying was being done, if they're just reading. And if it is just reading, then maybe it's just memorization, which I don't believe is that very much or is that effective for mastering or learning your subject. But we really can't know. We did run across a lot of issues with the data from the survey results, and also a lot of errors in the entries. It could be a lot of respondent error too. As you saw, my data points were greatly reduced by 1/3. So maybe that reduced the true representation of all Ventura College students for our testing here. But it was interesting to do this study. So hopefully maybe additional, once there is a larger sample size for this survey, it might create or might render different results. I could not tell you. But I enjoyed this, although I think I might have been a little bit more than was necessary. This turned out to be a lot of slides. But thank you so much for helping me understand a little bit of statistics. Hopefully it will help me in my area of study.